Étienne Sandier, who's going to be talking about logarithmic interaction for infinitely many points in the plane, Coulomb gases, and weighted Foucault sets.
Thank you very much, and thank you to the organizers for this very nice conference. Yes, so I will speak about configurations with infinitely many points in the plane. So the talk will not be pointless, hopefully. And so I drew some of the points, but not all of them, of course. And okay, so these points, to such an infinite set of points in the plane, we associate an energy. So the name of the game is that the points are plus charges, and they are set against a uniformly negative background. So you must imagine that the white stuff is negative charges, and the points are positive charges. And they interact with a logarithmic interaction. So one way to say that is that the energy is defined through the potential generated by the charges. So you solve Laplacian H is equal to a sum of Dirac masses at the point, and you subtract dx, which is the Lebesgue measure on the plane. And so, of course, such a solution exists. And then you define the energy to be the average over the whole plane of the gradient of h squared. So I put quotation marks here because, of course, this is not well defined, or at least it needs to be better defined. So, okay, so the average over R2 is simple. It's just the limit of the average over large balls. And as Milton said, well, h is not, the square of gradient h is not integrable. It's just short of being integrable. So what you mean by this, so h has a logarithmic singularity at each point, at each positive charge. And so what you do to define this quantity is that you regularize either by removing the infinite part. So this is what we did with Silvia Serfati. By the way, I didn't say that the results I'm going to present are joint work with Silvia Serfati on the one hand, and for the second part of the talk, joint work with my colleague Yuxin Ge from Université de Créteil. Okay, so that's one strategy, to remove the infinite part. The other strategy, which was done by Nicolas Rougerie and Silvia Serfati, was to just blur the Dirac masses. And so it's not exactly clear if these are completely equivalent. Nevertheless, they are equivalent for uniformly separated lambda. So lambda is the set of positive charges. And I would say it's uniformly separated if there is a minimal distance between two positive charges in the plane. Okay. So the first remark is that the solution to Laplacian H equals 2 pi delta lambda minus dx is not unique. It's unique modulo harmonic function. And so this means that the energy is not exactly well defined as is, because for general lambda you will not have a generic canonical solution to the equation. So you will have to take an infimum over all the solutions to the equation. However, there is one case which is very nice, which is a case of a periodic lattice of points. So you take lambda to be a periodic lattice generated by two vectors u and v, and you assume that the determinant of u and v is equal to 1. So in this case, there exists a periodic solution to this equation. And you can take this as the canonical solution. And in this way, you define w of lambda to be the regularized integral of the average of the gradient square of this solution over the plane. And in this case, you have an explicit formula for the energy, which is regularization of this series which is not convergent. So this is not convergent in the plane. Lambda star is a dual lattice. So it's a lattice as well. So this diverges, but you can regularize it in this way. You can also regularize it in other ways. It will give you the same result, and that's what you get for W of lambda. But in the general case, where you assume lambda to be just a subset of R2, a discrete subset, then you don't have a canonical solution, and you just define W of lambda to be the infimum of all these quantities for every solution of the equation. So it will turn out that it's interesting also to consider a relaxed version of this energy, and this is partly inspired by a paper of Alberti, Choksi, and Otto, which I will mention again later. And the relaxed version tells you that in the relaxed version you don't require this to be a gradient. So it's just a vector field J, which is not necessarily curl-free, and who satisfies this equation. So just the divergence is prescribed, but you don't impose that J be curl-free. So both W and W tilde are relatively well behaved on the set which I denoted A curly A, which is a set of subsets of R2 which are discrete and which have bounded density. If you don't impose bounded density, then things are not so nice. So you impose a bounded density at infinity. In particular, if you don't have bounded density, then you cannot have a well-separated lambda, right? If the density blows up at infinity, then the distances between the points has to tend to zero, at least for some points. Okay, so what do I mean by well-behaved? So one thing you have is that, so this is a result we proved with Sylvia some years ago, is that the minimum of W, and in fact W tilde as well, is achieved. So the proof, in fact, it's essentially, it was essentially due to Varadhan who told us, well, not exactly this, but who introduced us to this kind of reasoning. And so, by the way, I tell the young people in the audience, it's very important to have a good environment because in many instances of our work with Sylvia and other cases, it was important to have people, to discuss with people. And discussion with Varadhan was certainly very, very instructive. And, okay, so often if you have problems like that in the whole plane, the way you prove the existence of a minimizer or a solution is you take a big box and you solve in the big box, and then you make the box go to infinity. So certainly you could do this in this case, but you don't have to. And so the way you do it is, okay, so let's say, so I'm going to take you take a minimizing sequence of sets, lambda n, and as you recall, so the energy, I will write it on the blackboard. It's, okay, so it's the infimum of the so I write it like this because I don't want to go into the details of this regularization and limit as r goes to infinity. So it's the infimum of these quantities for J such that the divergence of J is equal to 2 pi delta lambda minus dx. So what I mean by delta lambda is just the sum of Dirac masses at the points of lambda. Okay, so you take a minimizing sequence lambda n, and you have a corresponding sequence of jn's which at least approach this infimum, and And so you remember that the integral over the average over r squared is defined as the limit of averages over large balls. So you also can take a sequence Rn going to infinity such that the average over the ball of radius Rn approaches the infimum. So in this way, you have a set of Jn and Rn such that the average of Jn squared over Rn approaches the minimum, which is alpha. Well, we don't yet know it's a minimum, but we will soon know it's a minimum. Okay, so then as n goes to infinity, you use Fubini's theorem in a very straightforward way. So you write this as a double integral. So it's the integral over the ball of radius Rn of the average over the ball of radius 1 centered at y of Jn squared. So this is almost an equality, except at the boundary you have some difference, but it's negligible as Rn goes to infinity. So then you have alpha, which is close to this, which is close to this, and now you write this in a different way. You write it as the integral over the average over the ball of radius Rn of a certain function of the vector field J, and integrated with respect to a probability measure on the space of vector fields. And here, the function of the vector field is just the average of the L2 norm average over B1. And the probability measure is the measure which makes every translate of the vector field with a center chosen in the ball of radius Rn equi-probable. So we write this in this way. So it's a measure, for instance, on L2 log of R2, R2. I wrote LP log because, in fact, J is not exactly in L2 log. And you put as a topology, you use the weak topology on LP log. Okay, so this is the thing to understand, is you take Jn and you shift it in every possible way so that the center is shifted to some point in the ball of radius Rn. And you make all these shifted vector fields equiprobable. And okay, so you write this like that. And then you pass to the limit. That's a mistake. I shouldn't have put here. No. Always mistakes. So yes. So what you should read here, I will write here. So it's the integral of f of j dPn of j. So now the n dependence is in this probability measure. So there is no ball of radius Rn. It's built in the probability measure. And so you can pass to the limit. You can pass to the limit. So the function f is lower semi-continuous. The probability measures modulo subsequence converge to some p. That's because f is coercive in some way. Okay, I don't go into the details. And then you get that alpha, the minimum, is bounded below by the integral of f dp. And now you use the Ergodic Theorem, because by construction, P is a translation invariant probability measure, because a shifted J is as probable as J itself. That's by construction. And you use and then the Ergodic Theorem tells you that, in fact, this thing can also be written as the integral with respect to P of averages over large balls of f applied to the shifted j's. And okay, so if you replace then f by what it was, you recover this, and then I wrote this, but this is wrong. So what I meant here by w of j, so what you get in the end is that alpha greater or equal to the integral of the average over R2 of j squared dp of j. And, well, this is very good, because then you just have to, since P is a probability measure, you just need to choose one j such that, well, which is less than the average over the probability measure P, and so you get a minimizer j. And in fact, you can prove also that P almost every j is a minimizer for your energy. Okay. So that's one result. The infimum is achieved. Another result is that if you restrict yourself to periodic lattices, so apparently out of habitude, how do you say habitude in English? I don't know. But out of it, I tended to use this notation W of j. So this is this quantity where you have removed the infinite parts. Okay, so if you want to, so if you want to minimize this energy among periodic lattices, well, you can, and the only solution is the what people call the triangular lattice. So it's a lattice for which looks like this. Okay, and you go on and on. So this is a regular hexagon with a point in the middle and reproduce. So this is a hexagonal lattice, and it's a minimizer of this energy. So that was a nice result. Well, for reasons I'm going to say. Well, okay. So one remark is that if this energy W tilde of lambda is less than infinity, so it's finite, then this limit, the number of points in a ball of radius r, so so again, there's a mistake here. So the number of points in a ball of radius r is roughly the measure of the ball of radius r if this limit exists. But the limit might not exist. So if you have an asymptotic density for lambda, then it must be 1 for lambda of finite energy. The other remark is that if you perturb lambda, if you perturb a finite set of points in lambda, then it doesn't change the value of W of lambda or W tilde of lambda. Okay, so now that I've presented the object W, I will give some motivations for it, because in fact it was not really invented by us, it was given to us by certain other things. So the first motivation, well, the first occurrence of it to us was in the study of Ginzburg-Landau vortices, which you heard about already. So if you consider the Ginzburg-Landau functional on a bounded domain, and you are in the regime where kappa, the Ginzburg-Landau parameter, tends to plus infinity, and where the applied magnetic field H sub E is proportional to lambda, is proportional to log kappa, then minimizers of this functional have some vortices which are typically uniformly spread in a subdomain of your domain omega, which depends on the parameter lambda, and which grows with the parameter lambda. So vortices in this domain, they interact not by the logarithm, but by the Bessel function. Well, not exactly the Bessel function, because you're in a bounded domain, so it's by the green function, which solves this equation. Okay, and there's also a repelling term from the boundary. But if you look at a smaller scale, at the scale where vortices are at finite distance from each other, then the scaling of this green function makes it happen that after blow-up, the interaction is Coulombian. So it's with a logarithm. And so in fact, one thing we proved in this setting is that if you take minimizers, or for that matter, almost minimizers of the Ginzburg-Landau energy, and if you blow up around the point in this subdomain where there are vortices, and you look at the vortices, then in the limit, so you will get vortices everywhere in the plane, and the configuration that you will get will be a minimizer of W, almost surely with respect to the point around which you do a blow-up. So that's a first occurrence of this energy. If you want, it governs the local arrangement of vortices in the Ginzburg-Landau model. The second occurrence of it was for what is called Fekete sets, or weighted Fekete sets. So in this case, you're looking at points which interact logarithmically. So they repel each other with a logarithmic interaction, and then they are confined by a potential V. So typically, V is norm to the square. So that's a classical potential, but you can use other potentials as well. And so it's known that if you minimize this with respect to x1, xn, and you look at the limit as n goes to infinity, so you can look at the limit at the macro scale. So this was done by Fekete, Polya, Jego in the first half of the 20th century. So in modern language, what you prove is that Wn divided by n squared, gamma converges to a functional I of mu defined on probability measures on R2, and which is roughly exactly the same thing, except that you don't need to remove the diagonal I equals j anymore. And so you have this limit, and in fact it was proved by Gauss, I guess, that you can characterize the minimum of this, and it was proved later in full rigor by Frostman, so that's in the 1930s, I guess, in his PhD thesis in Oslo, but it's written in French, so it's very good. And so that the minimizer for this is unique and can be characterized in terms of certain potential being constant on the support of the measure. Anyway, so, but now you can look at the micro scale. So what this result tells you is that the density of vortices has a limit. So you can look at this measure, and you get in the limit the density of vortices, which you can compute in some cases. Okay, but if you look at the micro scale, so what you would do is you would do a sort of blow-up in a point where the limiting density of vortices is non-zero. And what you will get is, again, a minimizer of your energy, W. So again, at the micro scale, the arrangement of vortices, I call them vortices because this is a school about vortices, right? but you could call them whatever you like. So again, the blow-up, the local arrangement will be governed by W. So if you take just almost minimizers of your function Wn plus V, this will be true for almost every blow-up. And in fact, Silvia Sarfati and Simona Rota-Nodari proved that if you take real minimizers, then this will be true for every blow-up limit. And they used techniques which were in this paper of Alberti, Ciocci, Otto. So they're very clever cutting and pasting techniques, very, very nice. Okay. So this can be extended to the logarithmic interaction of points on the sphere. So I'm very happy because several people talked about points on the sphere. And so this was done by my student Laurent Bettermin, and so one of the consequences is that if you take the logarithmic interaction of n points on the sphere and you minimize with respect to the position of the points, then the value of the minimum, you can expand it. So there's a term in n squared, which is explicit, but I didn't write it. It's well known. Then there is a term in n log n, which is a sort of scaling term, which is also explicit and well known. And then this type of result tells you that the third term, it's a term in n, and you can characterize it in terms of this minimum alpha. So if you knew alpha, which you don't, but you guess you know because it's probably given by this lattice. But if you knew it, then you would know this term. And in fact, there's a recent work of Brocha, Hardin, and Saf, who conjecture a value for this coefficient in front of n by some very, very different arguments, but their conjecture would coincide with this value if you believe that this is really the minimum of W. So that was very nice to find out. Okay. The third motivation for this energy is that of the Coulomb, is the statistical mechanics of the Coulomb gas. So you consider this measure here with the Wn, and beta, so is the inverse of temperature, and okay, so this is a measure over a very large space. Z and beta is the partition function, which makes this a probability measure. And so the type of results we got allows to expand the logarithm of Zn beta. So you have an n squared term. So this was known, n log n term. So this is a scaling term, not very exciting. And then you get n term with alpha in front of it. And you get a remainder term. So what we prove is not that this is negligible, but that this is negligible for low temperatures, which is reasonable because at low temperatures only the minimizers of Wn count, and so that's the type of result you can get. Okay, and there is corresponding moderate deviation, crystallization results for this problem. So again, it would be important in this setting to know the value of alpha and to know that it's given by this lattice. That would be exciting. Anyway, so now I'm going to talk about results that we obtained recently with Yushin Ge. So the question we ask is, when is W of lambda or W tilde of lambda, and we'll see it's not the same thing, when are these energies finite? Which is a relatively basic question, right? But why not ask it anyway? So we already know it's finite for periodic lattices, which have density 1. And so we wanted to know other cases, like can we characterize lambdas for which this is finite? And okay, so I will restrict now to uniformly separated lambdas. So because there can be two reasons why W of lambda become infinite. So one reason is that 2 points get very close together, so the interaction between the points. So I'm not interested in this because I don't know why. Well, maybe I'm wrong, but okay, so this I don't want to consider. And then, so the other reason why it would be infinite, it's because the points, the density of points does not approximate well enough the density 1. Okay, they are not well enough spread out. So this is the phenomenon I want to study, and this is why I restrict myself to uniformly separated lambdas. So points are forbidden to go too close to each other. Okay, so the first fact is that if you take the square lattice, z squared, and you remove a line, z, then you get something which has finite energy. So the proof is rather simple because you can compute the potential H in this case. So first you set V of z equals log of sine pi z. So this is a solution to this equation. You can check. And hence, you can, if you define H to be, okay, the periodic solution for the square lattice minus V, then you get a solution of this equation, and then you can compute this quantity and check that it's finite. It's not very complicated. And the reason for this is that if you look at V from a large distance, in fact, V is roughly like the absolute value of the second variable. So it's something like that. And you see that it has a bounded gradient. And so if the periodic solution for H has a finite L2 norm, finite average L2 norm, then if you subtract something like that, it will remain true. So quite simple. So where things get interesting is that if you now remove a half line, then you get infinite energy. So this is a bit surprising because you would think that W, well, that's what I told you, but apparently I was lying. What I told you is that W measures how well the points are spread out, how close they are to a uniform measure. So apparently this is not true because a half line usually, if you remove a half line, it should be better than removing a whole line. Well, that's not the case. That makes the energy infinite. But if you take W tilde, it remains finite. So you get two surprising things. First of all, that removing a half line is worse for W than removing a whole line. And the second thing you note is that these W tilde and W, well, they're not the same thing. And, well, to tell you why you could think this is surprising, you don't have to, but you can, because in particular this allows you to construct a vector field J such that the average L2 norm over the whole space will be finite, but for which there will not be a projection on curl-free vector fields which have finite L2 norm, average L2 norm. So this means that the Hodge decomposition in the whole space here does not work very well. Okay, it works very well if you take really the L2 norm, but if you take this average L2 norm, it doesn't work well at all. Okay, you don't have a way of doing the Hodge decomposition in a way such that the L2 norm is reduced. And it's worse than that. You cannot do the Hodge decomposition in the way that the L2 norm stays finite, this average L2 norm. Okay, so to prove that W of z squared set minus n is infinite, well, you do roughly the same thing as before. So this time the V is not as nice and explicit as before, but you can write it as a Weierstrass product. So you have a solution of this. You remove it from the periodic H. Okay, and you compute, and you find out that the average L2 norm over a ball of radius R, so quotation marks here always because I removed the infinite part, So this blows up like the logarithm of r. So you would say, yes, so when r goes to infinity, this tends to infinity, but you could say, well, maybe there is a better h, which would not blow up. But the thing is, singularity, the blow up is like the log of r. And therefore, if you add a harmonic function to h, you will never be able to remove this, this blowing up, right? Because this is rather mild. So you would have to remove a harmonic function which is rather mild and a harmonic function which is rather mild but it's constant. So it's not going to help you very much. Okay, so that's how it goes. So maybe now we're going to try to have a more general results. And so the result we have is that, okay, so if you take a uniformly separated lambda, and if you assume that the number of points in the ball, in any ball of radius r, is the right thing modulo an error which is r to the 1 minus epsilon, where epsilon is a positive number, then the w of lambda is finite. Okay, so you see that epsilon is equal to 0 is forbidden here because we have the example of z squared z minus n, which would satisfy this with epsilon equal to 0 but have infinite w. The other remark is that, well, you might know it or not know it, but it's a classical fact that if you take a periodic lattice, it satisfies this, I think, with r equal to 2/3 or something like that. R to the 2/3, so that would be epsilon equal 1/3 or something like that. So this condition includes periodic lattices. It's not empty. Okay. So the proof of this is that you construct a solution of this equation. Well, Laplacian h equal to this, and you do it by approximation. So you, for each point p, you solve this equation. So this will be the normalized Lebesgue measure on a ball of radius 2 to the k. So you have a compactly supported solution of this. And then you sum these things for every point in the lattice. And then you let k go to infinity. So you want to prove that the limit as k goes to infinity converges to the right thing. And it does, in fact. I think so, at least. So the way you see this is that you have convergence, is that you write un as a, how do you call this, domino type of thing. And you note that the difference here satisfies, let's call it f. It satisfies Laplacian f is equal to this. And because you assume that the number of points in the ball of radius r is almost the same, is almost the right thing, well, the right-hand side here will be very small. And, okay, then you can evaluate. So the Laplacian, you have an estimate for the Laplacian. You will have also an estimate for f, and you do lots of things. And then you find out that this converges. And to a solution of your equation, and okay, then you get that everything is finite. Okay, so this is not completely the end of the story. So you have a criterion for W, which cannot be improved in the obvious way because you have this counterexample, z squared z minus n. But you might want to improve things for W tilde, because for W tilde, in fact, z squared z minus n is not a counterexample to finiteness. So this is what we'll do now, and this is done by moving points. So how do you move a point? So if you have a certain lambda and you want to move a point, what do you do? So assume you have a solution of this equation for lambda, and you want to compute a solution of this equation with a point displaced. So you take a point in lambda, so you assume that it's far away enough from other points, and you take a point p prime, which is not too far from it. So you will solve this equation Okay? And then you define a vector field to be the gradient of H in the ball. So you solve this equation in a ball, and so you let J equal to this and 0 outside the ball, and you add J to the gradient of U, and so you get a solution of this equation with a new set of points where you have displaced the point P to the point P prime. Okay, so the point is that this thing is not a gradient, right? Because J is not a gradient. It's a gradient in the ball, but it's 0 outside. So it's not a gradient, but the divergence is okay because the normal derivative of H is 0. So, okay, so this construction will be very convenient to do things for W tilde, but not for W, because you don't have a gradient. And so if you do this construction again and again and again, you end up with the following proposition. So if you take two uniformly separated lambdas, and if you can make a correspondence between the points of lambda and the points of lambda prime in a way such that okay, if you obtain, let's say, lambda prime by moving points of lambda, but the distance at which you move the point is uniformly bounded, okay? So I take a lattice, not necessarily periodic, but a lattice, and I move the points, but I'm not allowed to move them at increasing and increasing distances. The distance at which I move them is uniformly bounded. Well, then the finiteness of W tilde for lambda is equivalent to the finiteness of W tilde for lambda prime. Okay? So moving points at uniformly bounded distances will not change the finiteness of W tilde. And the proof is that you apply this procedure to move the points, and it works. Okay, so a corollary of this is what I already claimed some time ago, is that W tilde of Z squared set minus N is finite. Why? Well, because you have a bijection between Z squared set minus N and Z squared obtained by you take I will do a little drawing. So you take so this line is not here in Z squared set minus N. So I take this quarter plane, I move it down, and of course they get a bijection between Z squared set minus N and Z squared, and so this proves that W tilde of Z squared set minus N is finite. But in fact, there is a very nice fact, which is that if you can generalize this by removing from Z squared not N but any A. And so the result is the following. So if I take a subset of Z squared, so the existence of a bijection which moves points at a uniformly bounded distance is equivalent to the fact that the number of points of A in any ball of radius R is bounded by a constant times R. So that's a very nice fact, and in fact it's a discrete analog of a result of Gilbert's strang, which is called in a paper called min cut max flow in the plane, and it's based exactly on minimum cut and maximum flow duality. And okay, so this is convex duality, which proves this fact. And a corollary of this is that if you take a set lambda, which is Z squared set minus something, then in fact this condition with epsilon is equal to 0 is sufficient to ensure that W tilde of lambda is finite. And well, I guess that's everything I wanted to say, so I'll stop here.